So to be okay. Let's firstly begin with a brief review of the information paradox. Just your story. Consider we have a pure state black hole preparing some state and do the unitary evolution. And as time going on, there will be some thermal radiation. And if we consider the entropy of the radiation, and in this setup, if we assume the radiation is just thermal as the calculation by Hawking, the entropy just grow. But in fact, we know that in the long time limit, after the more than half of the black hole radius, we should expect the entropy of the radiation decreases. So this is called a page curve. And in my understanding, the question, this information paradox is how we do a gravity calculation and see such a page curve. So the answer is not known until the last year, the end of the last year, and from with a contribution of many of the audience. So now we have some understanding of how to resolve it. But basically, the idea is to use the Ryu-Takayanagi formula. Basically, if you consider the system with a holographic bulk, you want to compute the entanglement entropy of a subregion of the boundary. And you need to firstly consider two terms. One is just the area term, the Euro area of the Ryu-Takayanagi surface. Another one is the contribution from the bulk quantum fields in this area. Then after extremolize this, the summation of these two terms, you may get different solutions to this problem. So important thing is to take the minimum for different possible extremal surfaces. And as explained in a series of papers, and in fact, this difference, in fact, the solution to the information paradox it depends on the identification of the new saddle points in the gravity in the replicated gravitational path integral. So let me briefly illustrate the idea using a slightly different setup as the previous one. For the evaporating black hole, here we consider the eternal case discussed in this paper, which is more closely related to our discussion later. So consider we have some quantum mechanical problem and coupled to a bus. And we prepare the full system, the coupled system, into a thermofield double state. This circle, we draw it as an imaginary time evolution. And the dual picture of this quantum mechanical system coupled to a bus is in fact consider the dual of the quantum mechanical system as a holographic bulk described by some ADS with some gravity. And this bus is non-gravitational and it's in some flat space. Instead of specify the quantum mechanical system or the bus, here in this paper, the gravity calculation, just assume there is a conformal field theory lives both in the ADS space or in the flat space. So there is a conformal field theory with a transparent boundary condition. So to see there is indeed a analog of the information paradox, we consider the entropy of the left bus union the right bus. So in this case, we need to identify the Takayanagi surface. In this 1+1D case, we are considering, in fact, the area term becomes the Dalton value at that point, and the first naive guess for the Ryu-Takayanagi surface is just these two endpoints. These two endpoints of the bus. So because these two endpoints are in the non-gravity region, so there is no Dalton value, and we just get a contribution from this bulk fields. So from these bulk fields, we can do the standard conformal field theory calculation and get the entropy and find its linear increase as did in this paper. So there is an information paradox in the sense that if we consider the mutual information between the left bus and the right bus, contains the three terms: the entropy of the left bus, entropy of the right bus, and minus the entropy of the left union right bus. However, the first two terms, since if you only look at the half of the system, it will be just a thermal ensemble. So these two terms does not depend on time. So if this entropy of the left bus union the right bus indeed increases as indicated in this line, this blue line, which is a calculation with this trivial RT surface, we will see that this mutual information becomes negative. This is contradictory with quantum information theory. So in this sense, it's an information paradox. So the solution to this kind of information paradox is identification of the new RT surfaces contains two additional points in the gravity region. So this kind of solution is called a solution with island. So let's do a very interesting analog. This is like you consider some electric magnetic medium and put some point charge on it, and then the medium behaves as if there is a additional charge inside of the medium. So here is something similar happens, like if you put two twist operators here, and then the gravity region behave like we have two additional twist operators within this gravity region. So in the long time limit, this two left twist operators approach each other, and the two right twist operators approach each other, and finally they saturate to the 2 times the black hole entropy, and the contribution from the bulk quantum field is small. So in our work, we want to study the analog dynamics for the entropy directly from the quantum mechanical point of view. So here we just specify our system, the quantum mechanical system coupled to a bus. So for the quantum mechanical system, we consider we have a SYK system, the Euro SYK4 system. Then we need to consider what kind of bus we are describing. There are in fact many different possible choices of the bus. Previously, these two works consider the SYK model bus with M fermions. Here, M is considered to be the same as the original quantum mechanical system. They both they both contain the n number of Majorana modes. In this case, they found there will be no transition like the gravity calculation in the canonical ensemble for the second Rényi entropy. However, if we consider the second Rényi entropy in the macro-canonical ensemble, there will be a transition. In our paper, we also consider the analog case where M is much larger than N. And we find there can be a transition even if we are in the canonical ensemble. However, for this talk, let's consider a model that is more directly related to a previous gravity picture. That is, let's consider some bus that's described by some conformal field theory. Here we just take the conformal field theory to be the free Majorana chain. For this free Majorana chain, we have, in fact, we have n copies of the Majorana chain. Each label, each index I are just independent. They do not couple each other by this chain. And then the central charge is just n over 2. Very importantly, recall that from the gravity calculation, this transition between different possible saddle points, in fact, appears at time scale of the black hole entropy over central charge. Here, for the SYK model case, the black hole entropy is of the order of n, and so if we want to do a large n calculation and see the transition, we should instead expect order 1 page time, and the central charge C should also be of the order of n. So here because we are using a large n bus, so this will satisfy the requirement. So our full model contains these two parts: the quantum mechanical problem, quantum mechanical system, the bus, and a coupling between the system and the bus. Here, our system is the SYK model, and for this coupling, we just assume each index I can hop to an individual chain, Majorana chain to the site 0, and different indices only couple set under this SYK interaction. We also assume the lattice constant A is 1 over lambda, and for very, very large lambda, here we have this factor of square root of lambda because we want this combination to be the correct continuum field theory operator for the conformal field theory.
Sorry, Pengfei, the bus it's a infinite line or it's half infinite line?
Yeah, in fact, here we are assuming it's an infinite line, but in fact, it does not matter. In the low energy limit, it will be the same because it only depends on the two-point correlator of the Majorana fields. Either infinite line or the half infinite line will give the same result, up to a factor of 1/2, like this.
Thank you.
So if we what we want to do is again similar to gravity to consider the entropy. Then we firstly involve the Sommerfeld double state in real time, because for the Sommerfeld double we can put either the evolution to the left system or right system. Here for simplicity we just put all the evolution directly to the left system. So if we draw the figure for this state, it will look like this. We just draw the system and the bus as a single dot instead of a 1D chain. And here I have some dotted line. The dotted line means there's an interaction. You can also view this as a equal time contour for the chi and psi system. You can copy two of them and contract the left and right bus, and this gives you the reduced density matrix for the SYK system. So for the second Rényi entropy, we just to copy two of them and connect them. Connect the bra of the first replica to the cat of the second replica and vice versa. So we can equivalently draw this left figure as the right-hand side by connecting a different chi contour that is connected together. So we put this contour of chi and this contour of chi together and to be a single contour. And then we can draw the left figure like the right side. Again, this dotted line means the equal time contour or the interaction between the and psi. We have these two different kind of drawing of the same figure. They will be convenient for different purposes. So sometimes we will use this one, sometimes we will use this one. So from this left figure, it is also obvious that we can this trace zero square can be considered as a correlation function between two twist operators applied on either on both the system, the left system and the right system. Equivalently, we can say it's a correlation function between twist operators for bus, but it will be useful to consider it as a twist operator applied on the system. So we want to do the pressing go for this contour. Instead, using the standard time in both the real and imaginary time plane. Here we instead use a single real parameter to parameterize the contour. Here we consider this as parameter. It contains both the real and the imaginary time evolution. Then it goes from 0 to 8t plus 2 beta. Here t is the real time evolution and beta is the imaginary time evolution. So we can label the counterclockwise from s equals to 0, and in the clockwise to the s equals to beta plus 40. And then we go from here again, the s equals to beta plus 40, then the clockwise to the 2 beta plus 8t. Then we need to specify how to deal with the imaginary or real or forward or backward real evolution. This is basically from this observation. For imaginary time evolution, we just have e to the minus hs. Well, for real forward evolution, have e to the minus ihs. For a backward evolution, have e to the ihs. So this means we just need to include the phase factor that is I. If it's 1 for the imaginary time evolution, it's I for forward real evolution, and minus I for backward real evolution. So we just include this phase factor in front of this Hamiltonian, and we can just treat everything as if this time integral is just a real time. It's just a real parameter. So with the disorder replica diagonal assumption, we can just write out the Schwinger-Dyson equation. There are 2 different contributions for the system. They can either hop to the bus, get a contribution proportional to the Green's function of the bus, or just using the SYK interaction and the standard Mellon diagram. Here, on each vertices, we have such a phase factor as explained in the last slides. So here in the Schwinger-Dyson equation, we have this capital F, which is defined as like this to take into account this phase factor. Also, this little g is in fact the Green's function of the bus. So if we do the numerical calculation for a self-consistent solution of these 2 equations, and then get the solution, we can use it directly to compute the second Rényi entropy, and contains the standard several parts. Its first part is the log determinant part for the system, and the free energy for the bus, the non-interacting Majorana fermions, and from the SYK interaction. So basically, the second term can be neglected because there is also a similar contribution from this Z. So the contribution will cancel between them, so we do not need to compute it. So let's see the numerical result first. So for the numerical calculation, we just set beta j equals to 4 and lambda over j equals to 5. So you see different behaviors if you consider a large interaction between the system and bus, or a small interaction with the system and bus. Recall that in the gravity calculation, we find we have 2 different set of points, and there is a transition at some finite time. Here, in the short time limit, we still have a relatively small entropy, and in the long time limit, it's saturated. However, whether we have 2 different set of points and whether we see this transition, it depends on we have a small or large v. So for a small v, we have a transition, have different set of points, and this is a first order transition, and we see 2 different set of point solutions. Well, for a large v, we do not see such a behavior. In fact, this is similar to this paper. This is a paper by Xiaoliang and Huan. They consider the eternal wormhole case. So in this case, it's similar. If you have a large coupling between the two sides, there will be no first order transition. However, if you have a small coupling between 2 sides, there will be a first order transition. So to understand why there will be a first order transition for small system bus coupling, but not for the large system bus coupling, let's look at the Green's functions for small v. So let's first recall how we label the contour. We label the contour start from this contour for bus psi, go from some point and wind clockwise. here we use a capital T to represent the total length of the evolution, including both the real and the imaginary evolution. So basically, we start from here, s equals to 0, and go clockwise to t/2 for the psi contour, and similarly, then start from here, from t/2, and one clockwise and to t. So then we can get a parameterization for the chi contour by focusing on the dashed line, the dotted line. It will introduce the parameterization for the chi contour. Basically, you see that the time from T/4 to 3T/4, the chi system forms a closed contour, and for the other time, the other time it forms another contour of the chi system. So firstly, let's consider we turn off the interaction between the system and bus, and this time there is no correlation between these two different, we call it different replicas. So then if we consider 2-point function, it's only non-zero if the 2 points are on the single replica. This corresponds to the this left figure for the Green's function. Here, this is the plot for the Green's function. This is a g t1 t2, and this axis is t1, and this axis is t2. So if we look at a single replica, this single replicas corresponds to this 4 small squares. And the other replica from T/4 to 3T/4 correspond to this center larger blocks. So this means if v is 0, we just have this replica diagonal parts of the Green's function. Then we consider a small v, and this short time solution is in fact perturbative. We can consider a perturbative calculation from v equals to 0. And then it will generate some small off-diagonal terms here, as shown in these light colors. For these areas, it will be proportional to v square for a small v. So this is very different from the long-time solution. In the long-time solution, we see that although these blocks are still correspond to the replica of diagonal terms, they are of the same order of the replica diagonal terms. So basically, you see this cross structure. This structure is similar to this block, this replica diagonal block for the short time limit. Basically, this states that there is a approximate cancellation between the forward and backward evolution of these two contours. These two parts, in fact, describe this from 0 to T/4 and from T/4 to T/2. So they correspond to 2 halves of the contour of the chi system that interact with the same precise system. This is similar to the result finding in these two papers. Where in the long time saddle, in fact, the different different contours get connected. Here, this time from 0 to T/4 and T/4 to the T/2, which is disconnected in the v equals to 0 limit, becomes connected in this long time saddle. So this, in fact, this explains why for large v we do not have a transition. In fact, because for small v we have a transition because we can distinguish these two different saddle points by saying, for example, we have a quantitative difference between the off-diagonal terms. It be small for a short time saddle, and it's be large as a diagonal term for long time saddle. However, if I have a large v, even for the short time, because these terms are proportional to v squared, for large v, they are already very large. So there will be no difference between these two solutions. It can be connected smoothly, so there will be no first order transition. They just the solution just changes from the one to the other very smoothly.
Pengfei, what happens in the microcanonical ensemble?
I haven't tried the macrocanonical ensemble. In fact, here we see this transition even in the canonical ensemble.
I guess that picture at the left, though, I mean, it looks like the energy is changed. That picture at the left, I think, is lower energy than the picture at the right.
But it's for it's for different times, so it looks like it's more. So sorry, what's your argument for
just the width of those features is wider.
Yeah, but this is basically.
Oh, you've rescaled the time, or?
Yeah, I don't rescale the time here.
Oh, okay.
Yeah, this is 1.5 beta, but this is 6 beta.
Okay, okay.
Yeah. It's a good question to consider the macrocanonical ensemble, but I haven't tried the calculation.
Okay.
So now we want to study the short time saddle and long time saddle in more details. Firstly, let's consider this short time saddle. In fact, this is as I just said, it's a perturbative result effect from the V. So for small v, let's consider doing a perturbative calculation. For small v, because for v equals to 0, we have the replica diagonal Green's function for chi. So for a small v, we can just focus on a single replica of the chi system. Then after we integrate out the precise system, this will generate some two-point correlation on the single replica. The term is non-vanishing if the 2 points are intact with the same bus. So means if these 2 points are both on the same side of this dashed line, it will be non-zero. However, we can compare this to the thermal ensemble. So for the thermal ensemble calculation to the same order, it will appear without any restriction. Any 2 points on this contour has a contribution for in the action. So if we consider the difference between these two, this can be computed by considering 1 point on C1 contour and 1 point on the C2 contour. So this is basically similar to the calculation in this early paper, and in fact, we can directly do the perturbative calculation by using the conformal Green's functions for this bus and also this SYK system. And there is an analytical formula for this, but it's quite lengthy, and I will not show it here. Here we just show it a long time limit. We can draw it and compare to a numerical result. Also, very interestingly, there is a factor of square root of beta. This is because the coupling between the system and bus in this model is in fact relevant, because the scaling dimension of the chi system is 1/4 and the scaling dimension for the precise system is 1/2. So we have a scaling for the V, and this V square times the square root of beta gives the correct scaling for this near this fixed point. So let's now look at the long time saddle point. For the long time saddle point, as before I said, it can be viewed as the correlation function of two twist operators. We still want to understand this, get some intuition from the Green's functions. Here, we draw both the real part of the Green's function and the imaginary part of the Green's function in the long time saddle. Excuse me. Let's compare it to the denominator when we compute the entropy. In the denominator, we have no twist operators, and the Green's function will look like this. So let's compare these two. We find they are almost the same for this diagonal blocks. Well, the main differences comes from this off diagonal blocks, where we have a diamond here, and we have 4 triangles there. these positions basically correspond to the place where we insert the twist operators in the contour. Here, for example, if we look at this diamond, the time is around 3T/4 or T/4. This is 3T/4, this is T/4. So this means the contour for T/4 is this point, and the 3T/4 is in fact this point. So this diamond structure corresponds to the insertion of the T right for this twist operator. Similarly, you can analyze these four corners. They correspond to the twist operator on the left. So from the Green's function, it seems the Green's function of the system get contributions from the left and the right twist operators independently. In fact, we can show this more straightforwardly by considering the numerical calculation with a single twist operator. If you just consider a single left twist operator as expected, we just have these four triangles without the diamond here. Also, we can consider we have a twist operator on the right system. For this case, we just have this diamond as expected. So this tells us the Green's function gets contribution separately, and then we can argue that this long-time saddle point satisfies such a factorization of twist operators. This is similar to the gravity picture where you have a 4-point function because you have 4 twist operators, and you take the OPE limit, and effectively this in the quantum side, this means we have a factorization of this 2-point function of the twist operator. So
can I ask a question? Could the energy be different though in the case where you have 1 twist operator versus 2 twist operators?
The energy?
Since you're in the canonical ensemble, there's going to be some energy that gets determined dynamically. It seems like it could be different in the computation with 1 twist operator versus with 2 versus 1.
Right, but at least from numerical calculation, I'm going to talk about this figure, and from this figure, it seems the energy will not change. Here, let me first explain this figure. Here, we just compare it to if this applies, then the long time entropy of the long time saddle will be the 2 times this thermal entropy. This is a subsystem entropy of the thermal system, the coupled system compared at the temperature 1 over beta. So we compare it with a numerical result at numerical saturation value of the entropy. So we find the matches Pratt-Will. So for different temperatures, I think this indicates that in this long time saddle, it will not change.
I guess maybe here it's important that the Majorana chain is infinite bass. So the temperature like forget at after it dissipated. So.
Yeah, it's possible. In fact, we also tried the case with the k bus and takes the m much larger than n, and similar things happen.
Sorry, if the size of the bass is like the same as SYK, then
no, much larger than the SYK. I mean,
yeah.
We also consider the case the bus is again a SYK model, but contains more number of modes.
Yeah, but if they are the same modes, then you will expect the energy change what Doug is talking about will be important, right?
Yeah. I think so. In fact,
so you could consider the case where the bath and the SYKs have different temperatures. And I guess the properties of the long time solution will be determined just by the temperature of the bath. Is that right?
Yeah, I think so. I haven't tried it explicitly, but I guess that's correct. Yeah, I think so. Okay. So now we want to see the information retrieval in the SYK model setup. So for here, it's an analog of the entanglement wedge reconstruction in the gravity picture. Basically, in the gravity, the entanglement wedge reconstruction means you have some some operators in the block, some information contains in the block within some entanglement wedge. Then we should expect it can be reconstructed using a boundary operators. Basically, for the present discussion, if we consider we throw some information into the block, consider we throw some particles moving towards moving the as this blue arrow, and then if we throw it before the page time, we first need to wait for the page time, and then the information of this particle can be reconstructed from the bus. If the time t is t naught, where we throw the particle is larger than the page time, then we just need this particle to approach this this island, and then we can extract the information. So we want to see the analog behavior in the SYK setup. So we need to perturb the SYK system and compare it with the unperturbed density matrix of the bus. So here we consider a specific operator for the perturbation, that is by this this unitary operator square root of 2 times the chi1. So this is a unitary operator. And we basically first involve the time t naught for the thermofield double state, and then apply this perturbation operators indicated by this cross. And then we involve time t. Note that since we are in fact involving the system by HL+HR, so when we after we have this cross, we need to put additional evolution t both to the left side and the right side of this cross. Excuse me. We then trace out the SYK system and compare them. Reduce the density matrix of the bus with or without this perturbation. There's two different types of the density matrix. This one with 2 additional insertion of the Majorana fields, and this one without the insertion of Majorana fields. We want to compare them. So to compare these two density matrices, we first very simple object is we just try to compute the overlap between them. We can also consider this as we have some very complicated operator that is ρB2, and we compare the measured result of this very complicated operator on this perturbed density matrix and the original density matrix. And or we can introduce an oscilla and to do the control operation. We firstly consider prepare it in the maximal mixed state, and then we have a controlled operation on this system plus bus, this thermofield double, and we trace out the system. So then the density matrix of the bus union this oscilla will be have the probability 1/2 for the system to be the ρB2, and the possibility 1/2 to be the for the system to be in the ρB1. We can then compute the mutual information between them.
I'm sorry. Can I ask a question? What is the information loss that you have just at the level of the field theory side here? I'm sorry, you said it before, but I'm confused. Why would there be information loss in purely in the field theory? Is it because of the averaging over the J's that happens in SYK, or is it for some other reason?
No, here we are considering because we have a SYK system, we put an operator directly in the SYK system. This as a perturbation, we see whether we can use the information from the bus whether we can just look at the bus to see whether we have made this perturbation. So this is what we want to look at.
He's asking if the information is recoverable in a subsystem. So the SYK is coupled to the bath, and he's asking whether the information is recoverable from just the bath. It's not like the black hole has completely evaporated. It's like a partially evaporated black hole.
But you're saying there's a version of this question that can be and is phrased just purely in the field theory coupled to the bath. We know that whole thing is fine as it is, but you're saying it's a question of how they interact and what you can learn from the bath itself.
Right.
Okay, and you're saying that maps to the normal information problem on the gravity side.
Yeah, I think it's related to this picture, this box picture. If you because we have a left hand side, this is the system and this is the bus. Then you throw some information in the system and see whether it can be reconstructed from the bus. For the gravity picture, if this particle gets into the entanglement wedge of the bus, then the information of this particle can be reconstructed from the bus. So I think the idea is similar. We have a system plus a bus and perturb the system in some way and see whether this perturbation can be known if we only look at the bus. And we are trying to do a similar thing directly in the field theory.
Okay, thanks.
Okay, so we compare this to density matrix using this theta. We can compute the mutual information. It's in fact the second Rényi version of the mutual information between this theta and the bus. So if we consider a very short evolution time, and then this rho b1 and rho b2 are just the same because these two factor cancels out, and then we have 1/2 plus 1/2, and we get mutual information is just 0. Or we consider a long time limit where this two density matrix becomes very different, and this factor becomes 0, and we get this mutual information to be log 2. Okay. So let's firstly consider the calculation directly for this density matrix overlap. In fact, it has a very simple identification as a Green's function of the Green's function for this complicated entropy contour. The basic idea is that if you compute the trace rho b1, rho b2, then we just need to contract this density matrix to this density matrix, and if we draw it, it looks like this with two additional operators here. For the denominator, we do not have this two insertion of operators. So in fact, we are just measuring the Green's function of these 2 points. And this factor of 2 is just because of the normalization. So if we draw out the Green's function, we are in fact looking at this component of the Green's function. So for the short time limit, because this forward and backward evolution, they are on the same replica, they almost cancels. So we have a very large value here. However, when the long time limit, because these two replicas interact with a different bus, so will not be connected, and we have a small value for this density matrix overlap. So here is a numerical.
Sorry to interrupt, but could you explain that again? Why is the density matrix overlap related to the value of G at that location?
Okay. So because the first density matrix of rho b1 is just such a figure, and if we want to compute the trace rho b1, rho b2, we just connect them together and get such a figure. If we just have two rho b2 connect together, we just have a previous contour for computing the entropy. This is just a previous contour. Here, if this rho b1 times rho b2, we have two insertion of the Majorana fields here. So this basically, this ratio is a Green's function because it's here we have two additional Majorana operator. Right. So furthermore, here as we draw here, because this is a specific time of this specific Green's function with these two times. So here we draw it which time it corresponds to. It corresponds to somewhere here. So it takes a very different value for short time saddle and the long time saddle. For the long time saddle, it approaches 0. And for the short time saddle, there will be an approximate cross structure here. For v equals to 0, this position, this should be strictly 1/2, and this 2 times g is just 1. But for some finite v, this will be slightly smaller than 1/2. So we have some smaller decrease. However, in the long time limit, it is very small. So more explicitly, we draw the numerical result like this. This left-hand side figure means we throw the information before the page time. Then there will be a transition. This is at the page time. So at the page time, because we have a transition of different saddles, so there is a first order transition. There is a drop of this overlap. Differently, if you consider a large T naught after page time, then this overlap just drops smoothly to 0. So this is expected in holographic theory. In fact, this is not really expected from holographic theory. For example, here, if we in fact create a particle directly move towards the black hole, then before the page time, we should know nothing about that information. We need to wait until the page time, then the information can be reconstructed from the bus. So so we want to understand what makes this difference between the simple holographic expectation of and our calculation. So basically, let's.
Sorry, could I ask another question? Could you go back one slide? Or actually 2 slides. What if I was computing trace row B2 squared? I would have 4 of those red X's.
Trace row B2 squared?
Yeah. Sorry, row B1 squared, row B1. I'd have 4 of the red X's.
Right.
But then would I conclude that the answer was proportional to, why in that case, sorry, why? In that case, wouldn't I have more Green's function? Right.
In that case, you have, in fact, I'm going to talk about it. This looks like this. So if you have row B1 squared, it have 4 operators, and to leading order of large n, you can do the Wick theorem.
I guess what's confusing me is, shouldn't trace row B1 squared be the same as trace row B2 squared? But in one case, it looks like we have some extra Green's function from the 2 red X's. So my question isn't very well.
Are you saying like you think the row B2 square should be the same as the row B1 square?
Yeah, I would think those should be the same. And
why is that?
Well, just because you didn't do much. I mean, you just the difference between those is just you added an extra particle in one case or something, right? So
if it takes the log of the trace row B1 square or the trace row B2 square, as the leading order of large n, it's the same. Because trace row B1 square or trace row B2 square are in fact is e to the n times some constant. So to the leading order of large n, they are the same, but there is a proportional constant.
Okay. I guess, but somehow the difference here, whether you have that Green's function or not, is a big deal because it goes to 0.
Right, right.
So it seems like naively they would differ by a factor of that Green's function, which doesn't seem like it should be right. Like they should be, if they're different, they should be different by some order 1 factor, not by some Green's function that's almost 0.
Sorry, you mean order 1 factor means?
Like a half or something like that. Well, maybe I'm wrong. Maybe it is much smaller, but I don't see why.
Sorry, it creates 1 particle, right? It's not just to have some small probability of putting 1 particle. Shouldn't you expect orthogonal to the 1-point function is vanished, right?
Well, but it creates 1 in the bra and the cat, so I don't see why trace row B1 squared should be so much smaller than trace row B2 squared. But my question isn't very sharp, so you should continue with your talk. See if I can improve it.
Okay. So here, to understand this behavior, we do a calculation using the effective action I mentioned before. So for the this calculation is for the short time saddle. So because we have identified the metric or density matrix overlap with this Green's function, so we just need to compute the change of the Green's function from this additional action. So here the change of the Green's function to the leading order is then just from this connected 4-point function. We take different possible assumptions for this connected 4-point function. We can either assume it's just satisfy the Wick theorem. So in this case, we are considering the effect that the particle can directly fall into the bath. This is because we get an intuition that the particle can only be extracted after the page time. One assumption is that the particle only falls into the black hole, but not go directly into the bath. But for the quantum mechanical system, we'll apply a particle operator on the boundary. There will be one mode into the box and another mode directly into the bus. So for this one, this assumption, we are in fact considering the particle is still free, but it can move either into the black hole or to the bus. So we can also consider a coupling to gravity. This means we consider this 4-point function as a Schwarzian 4-point function. In fact, this gives this dashed black line, which consistent with the numerical solution. So this coupling to gravity is the main reason for this initial decreasing of this of this matrix overlap.
Sorry, if you only have like chiral fermions, then probably you won't have this effect.
Yeah, but but it's hard to construct such sorry, the first effect will not be there if I have a chiral formula, but it will always couple to gravity. However, here from this consideration, our understanding that this coupling to gravity is the main reason for this initial drop.
What does the coupling to gravity exactly means to the boundary particle?
So consider because for example consider we are because it's just a Green's function of trace B2 square. We consider doing this second Rényi entropy calculation. Then the geometry will change. right? Because of
okay.
the twist operator. Then
Okay.
the Green's function of the particle, it will see the change of the geometry. So this type of effect will be the main reason that the density overlap decreases for the initial time. So yeah, similarly, we can compute the mutual information between the Scylla and the bus contains this additional quantity, contains the four Majorana Fermi operators. Then using the Wick's theorem result, we can draw it like this. The result is also consistent with our previous understanding. For the short time limit, it will increase the mutual information. However, there will be a large jump at the page time, and after which it will saturate. Similarly, if we throw the information after the page time, you will see this saturation. Is a smooth saturation. So okay, finally, I have a summary for the talk. We consider the SYK model coupled to Majorana chains. So we consider different coupling strengths between the system and the bus. For small system bus coupling, there will be a transition, and for large coupling, there will be no transition, which can be understood from the Green's functions. And we also see this special point of the Green's function correspond to the density matrix overlap. More we can draw it and see the different behaviors if we throw the perturbation before the page time or after page time. And we have understood this decrease of the matrix overlap at the short time limit. Okay, thank you. Thank you.
Yeah, thank you. Any questions?
I would like to understand this before the page time plot. Like why could you explain this again? In this case, shouldn't it be impossible to distinguish using the bath?
Here, we calculate it perturbatively to see the change of the Green's function because of this additional term in the effective action. So this basically like if you
that term is the interaction with the bath.
Right. The interaction. In fact, it's the same effective action when you compute the entropy for the short time cycle. And then that's an interaction from the bath. So you can consider just this original contour rho b2, and when you do this calculation for rho b2 square, the geometry will be different because it's a second Rényi entropy. So this change of the geometry will contribute to the change of the Green's function. So because this basically we are measuring the Green's function on this entropy contour.
Yes.
Yeah. So this gives this initial drop for the density matrix and overlap.
But that doesn't seem reasonable, right? That doesn't seem like the right thing that should happen to the information. Let's see. So you wrote a delta G. So So this whole expression here is equal to the G at this special point where the X's are located, right? That's what you're plotting.
After taking this tau 1, tau 2 to be a special point.
Yeah, and so way you're evaluating that perturbatively is you're saying that the coupling to the bath induces some small change in that you compute the correction to G using the 4-point function.
Right, right.
Okay, where the coupling to the bath is a small effect.
Right, because this is a short time saddle and we are trying to do a perturbative calculation.
But it sounds very weird, right? Like you have a SYK system, you modify it a little bit, and immediately the bath knows the difference. Like I thought that we're supposed to have to wait until the page time, right?
Yeah.
I wonder if this is, some question of the normalization of the. Okay, well, I'm not sure.
Yeah, I understand this, but you can you can consider this thing as a measuring rho B2, right? We have two different density matrix, rho B1 and rho B2, and we consider we measure some complicated objects, but there's still some operator on the bus. Yeah, we consider measuring rho B2, and this we find they are different, although this is complicated, but.
Sorry, if you guys are done with that question, I'm not sure if you are or not, but I wanted to ask another version of my bigger picture question, which Douglas addressed, which is, I mean, in the calculations of the page curve that I was aware of, you guys got that beautiful result, but it was also using rules that would give results for things like non-zero correlators of partition functions and stuff like that. So I guess my question is, is there a role for that? I mean, is that sort of issue arising here in any way? Because I gather that this is a calculation involving pure field theory coupled to bath saddle points that switch and so on, which is great. It looks very impressive, but I'm trying to understand a little bit better the big picture and how it relates to the previous story. So specifically, there was this issue of an ensemble of theories, not canonical ensemble, whatever, it was an ensemble of theories was coming up and all that. Does that have a role here?
You mean?
The Schwinger-Kaddish equation is after ensemble average, after disorder average.
So it is the disorder average that's playing the role of that thing here.
Here we have in fact we have assumed the disorder replica diagonal. I think that's under the assumption of the disorder in the system is self-averaged, and I mean, I'm not sure.
I understand it could be correct that it still works and it's self-averaging or whatever, but I'm just trying to understand if that's what this is showing or if it's.
Yeah, this is the assumption, I think, in this work, because we directly you assume the replica diagonal instead of directly do the replica trick in the disorder space. I mean, to do everything correctly, I mean, rigorously, we need to introduce additional disorder replica. And in that calculation, we could show whether the disorder replica is indeed diagonal or not. But we did not introduce that. We just assume that's correct. Yeah.
Okay.
Yeah, basically, that's. Let me see. Let me say here, because, for example, when compute the entropy, if we do not assume disorder replica diagonal. When we do the average over the interaction strength, there will be interaction dependence both in here, Z, and in this S. Also, what we want to compute is in fact the disorder average of this one instead of the exponential of this entropy. So there will be some all kinds of whether we can commute everything or not. Yeah, so that's
okay.
that's
Okay, thanks. So it's in there. That's
yeah.
In that plot of the eye, maybe the next slide, or yeah.
The
Why
eye?
do you plot? Sorry, the plots. Back one slide.
Okay.
Yeah. Why? One more.
This one?
Yeah.
Okay.
Why do you plot? Why is the denominator there trace of rho b2 squared instead of something like square root of trace rho b1 squared trace rho b2 squared?
In fact, yeah, I just take something simple because you're correct. We can consider, in fact, all kinds of combinations. But I think if we have one quantity that means they are different, and for me it seems they are already different. So, for example, because I think if this quantity itself is not one, it means rho b1 and rho b2 are not equivalent. At least to some order of the.
Well, but maybe they are related by a multiple.
But trace rho is one. We have normalized the. I mean, if we do not consider, if we assume the disorder replica diagonal, I mean, that problem we haven't considered whether this is correct or not. But if you under that assumption, all density matrix can be normalized by trace rho equals to 1, right? Because they are density matrix.
And in the next slide, you have calculated the mutual information between the axilla and the base, right? So.
Right.
So here you also see a small increase.
Right. I guess I was thinking if we divide by the square root of trace rho b2 1 squared trace rho b2 squared, then we'll have the same number of red x's in the numerator and the denominator. So the answer won't just like be 0 because of some fact that the correlator is small.
Yeah, it's possible. In fact, if you consider like that, I guess this leading order, this calculation, I mean, this leading order contribution will vanish. In fact, although here I have not shown that explicitly, even if you consider this second Rényi version of mutual information, this leading order change of the Green's function will not play any role. If you expand it to the leading order of this change of the Green's function, here this quantity does not have the contribution from that part. However, it will still increase. Yeah, but yeah, this is also very mysterious to me because you can consider we have different variables to compute, but even if other quantity is like we have other quantity that will behave like similar to the holographic picture, but here we still have this quantity saying the rho b1 and rho b2 are not the same. For me, it seems because we have, for example, we take that normalization of trace rho, then there is still some quantity saying it's not the same.
So you are saying for the mutual information, you don't have the correction from the Schwarzschild 4-point function?
Not this one, not this leading order calculation. This will cancel out. Saying for here, you can see there's a very large decreasing. It's a proportional to time in the perturbative calculation. However, here is I mean, you just see the numbers. It seems to be smaller, and in fact, this leading order contribution, this term will not contribute to that.
So that's good, right? That means that increase is not due to the different change of the gravity back reaction, but because this operator applied just like leaks to the bath, just like dynamically, not because of wedge reconstruction, but just can have chance go inside or go outside. Just have this small probability of going to the bath.
But I think for that, in my understanding,
if V is small, then that won't happen very much. So in the plot that he showed, mutual information gets big. And if it was just because of direct leaking, you would expect the maximum to be of order something proportional to V squared.
Yeah, in fact, here just
so it can't be direct leaking.
This red dash line, we are trying to think this as what is a direct leaking. So this red dash line is calculated by this, assuming the 4-point function is satisfies the Wick theorem. This means just free particles, but they can move here and there.
I don't think that conclusion. How can that be correct though? Like if it's not direct leaking, and if it's before the page time, then how does the information get into the bath?
Boundary states.
Maybe we can leave this question for later discussion, and I'll keep this Zoom open. Are there any other questions? If not, let's thank Pengfei again.